Hello, welcome back. Um, Today we're going to go through an example that involves a triple integral. Um, so as a reminder, when we are working on an example that has to do with triple integral, you need to take your region, and it's a three-dimensional region. You need to project it down onto either the xy plane, the yz plane, or the xz plane. Look at the projection and use that. Look for a good region, a region that's nicely defined, and then use that to find the bounds on your domain. So that sets up two of your integrals, and then figure out what the lower function and the upper function are. So we're working on this integral where we have to do a triple integral of x squared plus z squared dv, where E is a region bounded by a paraboloid, y equals x squared plus z squared, and the plane y equals 4. So again, remember, like this function, this x squared plus z squared, is kind of like the temperature or the density of some object, and what we're looking for is what's the total mass of the object, or what's the total amount of heat in the room. All right, so always the first thing to do is to draw a picture. So what do we have here? We have, let's see, y equals 4. So this is x, y, z. Y equals 4 is a plane that looks like this. And y equals x squared plus y plus z squared is a paraboloid, not a hyperboloid, a paraboloid that comes in this direction. And so how does this look? So this is this region. This is the region that we care about here. It's a region where, I guess, it kind of looks like a hat or maybe a ham. But let me get rid of all of these pictures. I'll redraw this picture, realizing what we want to do now. So the first thing we're going to do is we're going to try one projection, which is we've got this ham-like region. And what we'd like to do is we'd like to project it onto the xy plane. So if we project this onto the xy plane, what we're basically doing, is we are squishing this. We're projecting it down. We're trying to squish it so that it's completely flat, and it lies on the xy plane. And if you do that, then what we get is we get a shape. Right? We've taken this three-dimensional object, we've made a two-dimensional object, and the two-dimensional object is formed by this parabola and this line. So this is our D, whereas we've got this larger three-dimensional object is what we would call E. All right, so we now have an idea about how this looks. Let me see if I can make this work. Copy. Let's go to the next slide. If it'll let me. Okay. Paste. All right, so this is our picture. What we'd like to do is figure out how D is defined and how the upper functions and the lower functions are defined. So what is our D function? Our D is defined, so what we now need to do is we need to take this picture and put it into two dimensions. Right, where we have our x and y plane. And what we see, so this is going into the y direction. What we have is we have a parabola. All right, so this region isn't too bad. This looks like we'll need to take some vertical slices. All right, so our vertical slices look like this, where we're going to need to figure out where these things start and stop. So in the xy plane, then y equals x squared plus z squared becomes y equals x squared. And so if y is equal to 4, then x goes from -2 to 2. So we start chopping here at -2, and we stop chopping at x equals +2. And so this would be our domain. Our domain would be defined by x goes from -2 to 2, and y goes from this x squared up to 4. So this is our domain D. That's the two-dimensional object. And now we need to say, for any point in D, what is our upper function and what is our lower function? So we realize that those points are defined by our hyperboloid. So we're saying if we're here at any point in the xy plane, and we want to know what is the upper function, the one that's above the domain, and then what's the lower function, what's the function below the domain, then what we need to do is we need to say, all right, we need to know what is z as a function of x and y. So solve for z, and what do we get? We get z squared equals y minus x squared. So then z is equal to square root of y minus x squared, plus or minus. So this top one right here is z is equal to plus the square root of y minus x squared, and this bottom one is z is equal to negative square root of y minus x squared. And so what that means is that if we're going to integrate the triple integral of square root of x squared plus z squared dv, the inner integral looks like this. Integral from negative y minus x squared to positive y minus x squared of our function dz. And the outer integral, that's our red d function, we said we wanted x to go from -2 to 2, and y to go from x squared to 4, and so dy dx. And so this would be an integral set up where we've projected onto the xy plane. So that's an integral. How do we integrate this? Not easily, right? Because what do we have to do? We have to take the integral of this with respect to z. And that's not pleasant. It doesn't, like, the way you do that is probably some trig substitution. Would make your life really, really complicated. So what that's telling us is that's probably not the right way to set up this integral. And so you can just go, this was the wrong way to set up the integral. But it is the right, I bet if we put this in the Mathematica and said calculate this integral, it would give us the answer. But let's set this up in a way that we can actually do by hand. And that is to say, let's project onto the xz plane instead of the xy plane. All right, so in this case, and there's a clue. The clue that we should do this is that we look at these functions, and the hyperboloid, our paraboloid that is of interest is best defined by functions of where y is a function of x and z. And so that's a clue that maybe that should be the direction in which we project. All right, so we have the same region, right? It still looks like this hat or ham. And now we're projecting onto the xz plane. All right, so that takes this picture, and if we squish it onto the xz plane, then what we get is a circle. We don't get that parabola shape, we get a circle shape. So what did we have here? This was x squared plus z squared equals 4. And so if we take that, so if we have y is equal to x squared plus z squared and y is equal to 4, then that's x squared plus z squared is equal to 4. So we have this, our domain is now defined by x squared plus z squared is less than or equal to 4, greater than or equal to 0. So it's that circle. And then the higher and lower functions say, all right, so now we choose any point in our domain and we see, well, what's the lower boundary and what's the upper boundary of this, of our solid. All right, and the lower boundary is given by our paraboloid, y equals x squared plus z squared. And our upper boundary is given by y is equal to 4. And so if we're setting up this triple integral, then we get the triple integral of square root of x squared plus z squared dv is equal to the double integral over our circle times the single integral from from y goes from x squared plus z squared up to 4 of square root of x squared plus z squared dy and then dA. All right, so now we have an integral, and this integral, we can do the inner integral, right? There's no y available, so let's now do that integral. All right, so there's no y on the innermost integral, and so when we integrate, we get whatever it was times y, and y evaluates from x squared plus z squared up to 4, and so we get this integral of square root of x squared plus z squared times 4 minus x squared minus z squared dA. Now, how do we do this integral? So we could set this up as an integral from x goes from -2 to 2, z goes from the bottom half to the top half. But if you look at this, you should notice some circly things, right? We have the domain is kind of circly. We have a bunch of x squareds plus z squareds. And so you should think, wait, maybe the best way to do this is in polar coordinates. All right, so because this is easier to do in polar coordinates, let's set this up. We have our circle here, where we have x squared plus z squared is equal to 4. So in polar coordinates, that's saying r is less than or equal to 2. R is between 0 and 2. And theta is between 0 and 2 pi. And so what we get is we get an integral from r equals 0 to 2. Theta goes from 0 to 2 pi. And then x squared plus z squared, well, square root of that is just r. And then 4 minus r squared. And then don't forget, because these are pirate coordinates, we get r dr d theta. All right, and so what do we get? We have an expression, there's no thetas in here. So when we break this apart, then what do we get? We can just take the theta integral by itself, and then we can take the r integral by itself. And what do we have? We have 4r squared minus r to the 4th dr. This first integral gives us just 2 pi, and the second integral gives us 4r cubed over 3 minus r to the 5th over 5, evaluated from 0 to 2. So we get 2 pi times 32 thirds minus 32 fifths. So that's 64 pi times 5/15 minus 3/15, which gives us 128 pi over 15. And so what's the interpretation of this? The interpretation of this is that when you integrate, when you take the triple integral of this function, x, y, z, dv, you get this as your answer. So if this is equal to, for example, a mass density, then this is telling us what the total mass of that three-dimensional object is. All right, come back for another super tiny video related to these triple integrals. See you shortly.